Hello everyone. In this video, we're going to go over the sections 5.1 class node problems. So first, this section is a lot of computations that has to do with sequence. It's going to be kind of brief. So for the first question, we have brightify terms of each of the following sequences. So we have an equals to n plus 1. So this is very similar to the one that we saw on the introductory video. But so a1 will be 2 times 1 plus 1. Remember, the index that is here is being plugged where the n is. So we have 2 plus 1, 3. And so that's the first term. The second term, I'm going to plug 2. 2 times 2 plus 1. And so I get 5. The third term is 2 times 3 plus 1. So 6 plus 1, 7. The fourth term is 2 by 4 plus 1. So 8 plus 1, 9. And a of 5 will be 2 times 5 plus 1. So 10 plus 1, 11. So the first 5 terms will be 3, 5, 7, 9, and 11. Okay, so once again, notice that we're taking the index and then we're plugging it where the n is. Now, notice that this index starts at n equals 1, but this one is going to start at 0. So when I do the first term, it's going to be b0 actually, and that's going to be 0 squared minus 0. So in this case, it's just 0. B of 1 is just going to be 1 squared minus 1, which in this case is also 1 minus 1, 0. B of 2 is going to be 2 squared minus 2, so 4 minus 2. So 2. B of 3 is going to be 3 squared minus 3, so 9 minus 3, which will be 6. And last, the fifth term, which will be before here, will be 4 squared minus 4, which will be 16 minus 4, which will be 12. So with that, I have the first 5 terms, 0, 0, 2, 6, and 12. Now for C, we have something of the form minus 1 to the j over j. Notice that j starts from 1, and it makes sense because we have a denominator, so we cannot divide by 0. So C of 1 is just going to be minus 1 power to the 1 over 1, which is just minus 1. C of 2 is minus 1 squared over 2, which is going to be 1/2. C of 3 minus 1 to the 3 over 3, which is just going to be minus 1 over 3. C of 4 is just going to be 1 over 4. And finally, C of 5 is just going to be minus 1 over 5. You can kind of follow the pattern of how every time that we have an odd, we have a negative. Every time that we have an even, we have a positive number. When we have d to the n being 2 to the n for n that starts at 0. So d1 is clearly 2 to the 0, which is 1. Or this is d0, sorry. d1 will be 2 to the 1, which is 2. d2 will be 2 to the 2, which is 4. d3 2 to the 3, which is 8. And d4, which is 2 to the 4, in this case will be 16. All right, so let's move to question number 2. In question number 2, we're trying to find a explicit formula for each of the sequences. So this is pretty much looking for the pattern. So in here, I want to say the n term, right? A of n is something in terms of n. So in this case, we can see this is 2, 4, 6, 8, 10. So if I'm doing n, this is going to be 2n. When n that starts at 1, n bigger or equal than 1. Notice the first one is 1, the second is 4, the third one is 6, so on and so forth. So this describes this sequence. Now we have 1, 4, 9, 16, 25. Notice that these are squares. 2 square, 3 square, 4 square, 5 square. And this is just 1 square. So pretty much we can say an is going to be n squared when n bigger than 1. We double check. A of 1, 1 squared, 1. A of 2, 2 squared, 4. So making sense. Okay, so now we have 1 minus 2, 3 minus 4, 5 minus 6. So this is like the numbers. So an is just going to be the number n. But we have a minus 1 in front. And it's a minus 1 with the even numbers. So let's say that we're going to start at n equals 1. So we want that when this is 2, I get a negative. So I'm going to go with n plus 1. Yeah. So when n is equals 1, I get a square, and it's positive. When n is equals 2, I get minus 1 to the third, and I get a negative. And so this is a good representation for this. Now for d, an, we have a fraction, and we can see the variation. The top starts 1, 2, 3, 4. So we can go with, if n is bigger than 1, we can go with the top being n, right? 1, 2, 3, 4. And the bottom is going to be n plus 1, since it's 2, 3, 4, 5. And so in this way, we're able to represent the n version of this. Okay, so now we did a little bit of first terms and n term for a sequence. So let's go with summations. So let's compute each of the following summations. So every time that you're doing this, you got to remember what the sequence is, and then make sure that you're adding from this specific term up to this specific term. So here we have 1, k equals 1 is 1, plus k equals 2, plus 3, plus 4, plus 5. So this is the sum from 1 to 5 of these elements. So now if I need to find the actual value, this is 3, 6, 10, 15. Now we have the sum of the first 4 squares. So we have 1 square plus 2 square plus 3 square plus 4 square. And so this is 1 plus 4 plus 9 plus 16. If I add this, this is 10, 14, and 16 is going to be 30. Now we have the sum of the first 4 2 to the j, starting from 0. So we have 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus 2 to the 3. And so now this is 1 plus 2 plus 4 plus 8. And so we have that this is 10, 15. Now for the summation from 2 to 6 of 2k minus 1, notice that we're starting at a different point. We started at 2. So our first one is 2 times 2 minus 1 plus, and then we go 2 times 3 minus 1, 2 times 4 minus 1, plus 2 plus 5 minus 1, and then 2 times 6 minus 1. And so this is 4 minus 1 is 3, plus 6 minus 1 is 5, plus 8 minus 1 is 7, plus 10 minus 1 is 9, plus 12 minus 1 is 11. So it's the sum of 3, 5, 7, 9, and 11. Okay. Similarly, we can do the following products. So the products of k, so that will be 1 times 2 times 3 times 4. And remember, this is equivalent to 4 factorial. Then we have here the multiplication of 2 to 5. And so this will be 2 times 3 times 4 times 5. Since this is almost like the same that multiplying by 1, you can also say that this is 5 factorial. And if we have 2i plus 1, like in this situation, remember we plug first in 1. So we have 2 plus 1 times, and then when I is equals 2, we have 4 plus 1. And then when it's 3, we have 6 plus 1. This is 3 times 5 times 7. Okay. All right, so hopefully that clarifies how sums and multiplications work. Now let's simplify a little bit factorials, since we want to be able to compute with this. So 5 factorial is, once again, this multiplication up to 5, right? So if you multiply what this is 6 by 4, 24 times 6 is 120. Now, if we have 7 factorial over 5 factorial, we kind of saw this before on the slides. In the slides video, this is just a multiplication 1 times 2 times 3 times 4 times 5 times 6 times 7. And here we're going to have the multiplication up to 5. So notice that I can pretty much cancel all these terms, and I'm only going to be left with 6 times 7, which is 42. Okay. Notice that this is equivalent, this piece here is equivalent to seeing this as 5 factorial times 6 times 7 over 5 factorial and canceling out the 5 factorial. Now, a factorial over 3 over 5, once again, we can do kind of the same thing. So we can do, this is 8 times 7 times 6 times 5 factorial over 3 factorial times 5 factorial. So I can cancel out this. Now, 3 factorial is the multiplication 1, 2, 3. So that's a 6. So I can put a 6 here, and we get 8 times 7 times 6. So I get to cancel the 6, and this is 8 by 7. So 56. 10 factorial over a is kind of the same thing. 10 times 9 times a factorial over a factorial. So you can cancel this out, and this is 90. So this is the typical type of calculation that we do with this. Now let's do a telescopic sum. Remember, telescopic sums, they're going to give me the first minus the last term. So this was pretty much going to be plug in 1. So you're going to get 1 minus 1/2, right? Well, really, this is going to be 1 minus 1 over 10, since this is the last one. 1 over 11, because this is the last one. And so this is 11 over 11 minus 1 over 11. So this is 10 over 11. Now, why this is going to be that? So let's back it up once for a moment and see once again how this behaviors works. So if we plug in 1, we get 1 minus 1/2. Then k equals 2, we get 1/2 minus 1 over 3 plus, in 3 is 1, 3 minus 1 over 4. And so plus, 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 plus. And so we're going to get here now 1 over 10 minus 1 over 11. But you notice that all this cancel each other. And so at the end, this is going to cancel this, and I'm only going to get 1 minus 1 over 11. Okay? So that's how telescopic sum, that difference between this is what makes the difference. But if you're not sure if something is telescopic, the best way that you can approach it is do the terms. Do the terms and see what's going to survive at the end. Okay. So now let's talk about a little bit of notation, going back and forth with the sum summation. So it says, write the following summation using summation notation. And so as you can see here, we have sum of cubes, 1 cube, 2 cube, 3 cube, and cube. So this can be represented as the sum from I equals 1 up to n of I cube. You see, when you plug I equals 1, you get 1 cube. When you plug 2, 2 cube, and then you reach up to the point where it's n cube. Now the opposite, let's expand. If we have k over k plus 1, going from k equals 1 to 5. So this is 1/2 plus, when k equals 2, 2/3, when k equals 3, 3/4, when k equals 4, 4 over 5, and when k equals 5, then 5 over 6. So this is what that expansion will be, what that sum will be. So now says, prove that from k equals 1 to n of k is equals n times n plus 1 over 2 for n equals 1, 2, 3, 4 by direct computation. So this is pretty much proving cases. We're just checking, we're not checking the general identity, we're just checking for these numbers. We're checking that that is true for this. And so notice that for n is equals 1, the right side is going to be 1 times 1 over 2, which is 2 over 2, which is 1. And the left side, of course, since it's just the sum from 1 to 1, is just going to be 1. So it works. For an n equals 2, the right side is going to be 2 times 2 plus 1 over 2. So you can see that this 2 cancels, and we get 3. Now, by the left side, we have the sum of 1 plus 2, which is 3. So same thing. Now, for n equals 3, the right side, we have 3 times 3 plus 1 over 2, which is 3 times 4 over 2. So that's going to be 6. 3 times 4 is 12. Divided by 2, 6. And now let's the left side, notice that is 1 plus 2 plus 3, which is 3 plus 3, 6. So works also. And similarly, we can do last, we can do n equals 4. So the left side is going to be 4 times 4 plus 1. Sorry, the right side over 2. And so this is 5. 5 by 4, 20, divided by 2, 10. And now the left side is the sum of 1 plus 2 plus 3 plus 4, which is 6 plus 4, 10. So also works. So with that, we just prove all the first, that this works for the first 4 cases, n equals 1 to 4. Now, this says find the value of n if k equals 1 to n is 55. So once again, this is something that you do by doing the formula of this. This is n times n plus 1 over 2 equals 55. And then you can see this as n squared plus n equals 110. And so you can do n squared plus n minus 110 equals 0. And then you can solve this equation to find what numbers will work out. So this is n minus 10 times n plus 11, right? And as you can see, the sum of this is going to give you 1. The multiplication is going to give you minus 110. But this only can give me 2 options, n equals 10 or n is equals minus 11. Since these are integers, minus 11 is not going to work out, so n got to be 10. Now, this here is just a reminder of the simplification of the factorials. So if you have n plus 1 factorial, just remember that you can see this as n plus 1 times n factorial. So you have n plus 1 factorial over n plus n factorial. You just do divide those 2 and you get n plus 1. Now, write using product notation. 2 times 4 times 6 times 2 to the n. Well, you can probably guess that this is just going to be the pi from I equals 1 to n of 2i. Just 2 by 1, 2, 2 by 2, 4, and you keep multiplying this until you reach the end. All right, so last, let's see some true and false question to finish here this section. So we have the sum of k equals 1 of c is cn for any constant, and this is true. By properties, notice that you can move this out of the sum, and this is c times the sum of 1 of k equals 1 to n. And so the sum n times of 1 is just going to be n. So this is c times n. So because of that, it's done. Now, the multiplication of the integers from 1 to n is n factorial. This is true. This is pretty much the definition of what the n factorial is. And now n factorial square is just equals to 2n factorial, and this is not true, okay? So for example, n equals 3. N equals 3, you get 3 factorial square. 3 factorial is 6, so this will be 6 squared, which is 36. But now, 2 times 3 factorial will be 6 factorial, which is definitely not 36. This is actually going to be 720, which is different from 36. Okay, so these are all the exercises for the introductory section 5.1.